Okay, so let's see this in action. So example 2, we've got the form something squared plus something squared. So this is definitely going to be a tangent substitution. So let x equal 2 tan theta. Find our differential. So dx is 2 secant squared theta d theta. So then we can substitute this in. Integral square root of. Now we know what this is going to turn into. How many steps you choose to show here is up to you. Some people show, in my opinion, a painful number of steps, too many, way too many, but also going right to what it transforms into is not very illuminating, and if you have other mistakes, then it makes it really difficult to see what somebody's doing, to even try to give somebody partial credit if this is on an exam or some sort of graded material. So for me, I usually would do this. I'd make this 4 plus 4 tan squared theta. And then a lot of times I'll do something like this. And I'll show that that's a 4 secant squared theta. And then in the next line, I'll take the square root. Okay, so that's the inside. And then, or you can even do this. Maybe this is even better. Again, this is completely up to you how you want to handle it. I'm always just wondering what's the best way to show here. What's going to make it easier to see. So that, I think, is a little bit more clear. So I'll go with that. Then we have our dx, which is 2 secant squared theta d theta. Okay? So then we take our square root. So that's a 2 secant theta times a 2 secant squared theta d theta, which is a 4 integrals of secant cubed theta d theta. So this one right here is an integral that you do not need to memorize. This was covered in, for me, if you have access to my lecture notes, this is shown in 7.2. So if you read those notes, you'll see how you can actually write this one out. So really briefly here, let's actually write this down. So I'll do this in blue for a second. So shown in 7.2 is the integral of secant cubed theta d theta. This one's a long one. This is 1/2 the quantity secant theta times tangent theta plus the natural log absolute value secant theta plus tangent theta plus c. That is the antiderivative of secant cubed. Now, I'm going to pause this and double check that I have my 1/2 in the right place. Okay, I just checked, and yes, that is correct. I sometimes forget where I put this 1/2, but that is the correct placement. So that is something that you do not have to memorize. It is just something that you can use when it shows up. On the exam, you'll have a formula sheet that you'll have access to, and it's also open resource for exams. And this is always given in a Calc 2 class, at least where I teach. Okay. So we can go ahead and fill this in. Of course, when we multiply this 4 by this 1/2, we'll get a 2. So that's why I'm going to write a 2, not a 1/2. So 2, and we've got this big old nasty expression. So this is 2 times secant theta tangent theta plus natural log absolute secant theta plus tangent theta. Okay, plus c. So we're not done yet because, of course, this is written in terms of theta, but we want to go back to x. So here's what we're going to do. To go back to x, we'll have to take a look at the following. We're going to use our substitution from the very beginning. So this is really going to tell us absolutely everything that we need to know. In particular, it tells us, it tells us two things. The first thing it tells us is we know what tangent of theta is. So tangent of theta is x over 2. Second thing it tells us is using the fact that we know what tangent is, expressed as a ratio, we know that this is the adjacent over hypotenuse. So that means on a triangle, if we draw a triangle, place your angle theta anywhere, obviously other than the right angle, so just pick an angle. And then relative to this angle, we have the opposite, which is x, and adjacent is 2. Therefore, the hypotenuse, using Pythagorean theorem, is x squared plus 4. What's nice here is this triangle should agree with what you were integrating. If you go all the way back to the original, you should have something like the third side of your triangle showing back up in your problem. If you get something way off the mark here, then there is some sort of issue someplace. Where exactly? Not entirely sure. Would have to look at, have to take a closer look at your own work. But yes, ultimately that would be some sort of sign that something's wrong, or in this case, a confirmation that good things are happening. Okay, so now, like I said, this number 1 tells us how to replace this tan theta and this tan theta, but we need to know what secant theta is. So in the case of secant of theta, this is no different than 1 over cosine of theta. And we know that cosine of theta is the ratio adjacent over hypotenuse. Well, since secant is just a reciprocal of this, that means secant is the ratio hypotenuse over adjacent. Okay? So because of that, this implies that the secant of theta is square root of x squared plus 4, hypotenuse over adjacent, so over 2. So then all of this can be used to rewrite. So to go back to x. So in this case, we have, let's go back. This would become 2 times the quantity. If we multiply secant of theta by tangent of theta, we would have x square root of x squared plus 4 all over, what's that going to be? Over 4. Plus the natural log absolute. We're adding secant and tangent together, but they already have a common denominator, so this would be x plus the square root of x squared plus 4 all over 2 plus c. There we have it.